All right, we're going to be moving along with logs today, more logarithms like we did before break, but we're working with common logs and natural logs today and some log models that we'll get into as well. So there's our objective, like I just said, common logs, natural logs. We've got to figure out what those are first, and then that'll help us solve some different types of problems. So this is key. I think you've seen this a little bit, maybe just a time or two in some of the homework. But a common log is a log with base 10, and a natural log is a log with base e. And so anytime you see a common log, it's going to be written without the base 10 there. So it's just going to be log of x. This right here is a common log. Anytime you see a logarithm that does not have a base, it means it is base 10. And this right here is a natural log. That is ln, not in, ln, and that is log base e. So ln means base e, log means base 10, and that's where we're going to use those to, like I said, solve and go through some stuff. So here's just some calculator practice. You can get this by typing some stuff straight into your calculator. The log button is right next to the 7, and the natural log button is kind of right next to the 4 and the 7 on your calculator. So log of 124, I'm just hitting log and then 124 with your calculator. And you should, again, just use this as a calculator check. You should get 2.0934. The next one, log of 0.013529. And this ends up being negative 1.8687, something along those lines. Here's natural log practice, same type of thing, 28.69328. And that ends up being 3.35. Call it 6.7. Now this next one, natural log of negative 0.438. If you type that into your calculator, you're going to get an error, and it says it's a non-real answer. That's what my calculator says, at least. And what that's looking for is, again, think about what this is. So I would set this up another way: log base e to negative point. Oh, let's go back a second. Negative 0.438 equals x. If I'm setting that up in an equation, it would be e to the x equals negative 0.438, and e to what power gives me a negative number? None. So that's not that way. That's why that shows up as an error. That's why that's not possible. Moving forward, just going back to properties, which one of these are equal? I would say both b and c are equal here. Again, this cannot be reduced, but when you are dividing the arguments, you can separate those into two separate logarithms. A couple more to solve, and this goes back to what I told you at the beginning, what I'm going to say all chapter long. If you have one logarithm, you want to write it as in exponential form. So natural log of x equals this. In exponential form, my base is e. So e to the negative 0.5. Let's try this again. Sorry about that. Negative 5.062 equals x. Now you have an e button. That's the second natural log button. So again, right next to the, kind of right in between the on the left side of the 7 and the 4. So I'm going to go second natural log on your calculator, and then it should give you the e with the exponent there, and just type in negative 5.062, and you should get 0.0063, we'll say. Now, if you notice how we set this one up in exponential, this ends up being this exact same thing here in 7 that we saw in 6. So again, x would equal 0.0063. Very similar to number 8 as was to number 6. Again, no base, so that means my base is 10. So setting this up in exponential form, 10 to the 12.0821 equals x. Now, if you hit the you can plug this in however you want in your calculator, but if you hit the second and then the log button, it gives you the 10 to raise to the exponent power. And plug that in, of course, and you're going to get, and it makes perfect sense in scientific notation, 1.208 times 10 to 12. So that's, again, just some calculator practice on that previous slide, and some calculator practice here, but just making sure you set it up in exponential form properly first. Now these next examples, we're going to get into some decibels and some earthquake readings. So decibels, again, you can, as it says here, very wide range of intensities, so we're going to use logarithms to make that better. You can go ahead and read this up here if you'd like. This is the type of equation that would be given to you on a test or quiz. So D equals 10 log I divided by IO, I sub O, I naught, whatever you want to call this. What this is a constant. So I sub naught, or I naught, I sub 0 is 10 to the negative 12. So that's going to stay the same in this next problem. So again, I'll write the formula out here for you. Cooperates, there we go. D equals 10 log I divided by I naught. So find the number of decimals of jackhammer with a sound intensity of 3.2 times 10 to the negative third. So that's the intensity right there. 3.2 times 10 to the negative third. Compute the answer for two decimal places. So let's go D equals 10 log 3.2 times 10 to the negative third. And again, this I naught was from that's the constant, I sub 0. So you can plug this straight into your calculator. And like I said, plug this straight into your calculator as is, and you should get 95.05. And this is watts per, I guess these are measured in joules maybe. So 95 joules or decibels was, I didn't do it. Oh well, I think it's measured in joules. Regardless, let's move on to another example. Here's talking about earthquakes. Again, another formula that'll be given to you. So 2/3 log E over E sub 0 E naught. There's our constant again, 10 raised to the 4.4. So an earthquake in central Chile released approximately 1.26. There's my joules. I was wrong with decibels. Whoops. 1.26 times 10 to the 16 joules of energy. What was the magnitude in the Richter scale? Around 2 decimal places. So again, here's our formula. We had our E, or is 2/3 log E over E naught. This is our magnitude. So same thing, plugging this all into your calculator. So I'm going to get 2/3 log 1.26 times 10 to the 16th over 10 to the 4.4. And again, enter this straight into your calculator, and you should get 7.80, and that's just a reading on the Richters. We'll call it Richters. I think sounds like the perfect unit to me. So let's go back here. This is not joules, just decibels. Yeah, nothing more than decibels. So one last one. Here we have to think a little bit. If the energy release on one earthquake is 1,000 times the energy of another, how much larger is the Richter scale reading of the larger than the smaller? And so what we have to do here, we have to think about, again, to find the Richter scale reading is going to be we'll say R sub 1 minus, or we'll say R sub B for the bigger one, minus R sub S for the smaller one. This is going to give us how much bigger the bigger one is than the smaller one. So we have two separate equations that we have to work with here. We'll say here's the first earthquake, and here's the second earthquake. So one easy way to go through this is just to plug in a number. We're talking about the energy release, so the scale reading is not 1,000 times bigger. The energy release is 10,000 times that of the other. So if I'm going to say my energy for the first one, energy sub 1, we'll just say that is 1. So the energy that's going to be 10,000 times that for we'll call it energy 2 is going to be, I'll just put 10,000 times 1 is 10,000. And so now we're setting up our equation with these two energies. So my first one, the magnitude is going to equal 2/3 log of 1 divided by 10 to the 4.40. Second one over here is going to be magnitude, we'll call this 2, call this magnitude 1. And so that's what this turns into. This ends up being magnitude 2 minus magnitude 1. Same type of thing, 2/3 log of 10,000 divided by 10 to the 4.40. So plug both of these into your calculator, and after plugging both of these in, you get a magnitude 1. We'll say this is negative 2.93 repeating. Over here, magnitude 2 is negative 0.266 repeating. So magnitude 2 minus magnitude 1, this is negative 0.266 minus negative 2.933. We all know what to do when we have minus and negative, plus positive. So add those together, and you get a reading of 2.66 or 2.67. We're going to round nearest hundredth there. So the bigger earthquake that is 10,000 times that of another in energy released. So the magnitude reading is going to be 2.67 Richters larger, or 2.7 or magnitude is 2.67 times greater than that on the Richter scale. So yeah, that wraps up this section, and we'll go ahead and try the homework, and we'll move on with the next lesson when I get back.